Welcome back, everyone. Today, we're unlocking the secrets behind one of the most astonishing fields of modern engineering. We're talking about guidance, navigation, and control systems. In this explainer, we are going to completely demystify the brilliant and honestly almost unbelievable engineering behind guided missiles. If you've ever wondered how on earth a device traveling at supersonic speeds can perfectly hit a target from thousands of miles away, well, you're absolutely in the right place. We're going to break down the entire taxonomy of precision right here, right now. Okay, let's kick things off with a truly wild fact. Long before radars, microchips, or GPS even existed, this highly technical military field actually began as 19th century science fiction. No way, right? But it's true. The legendary author Jules Verne was literally writing about rocket-powered missiles with target seekers and proximity fuses all the way back in the late 1880s. So what started as pure, unadulterated imagination actually laid the conceptual groundwork for the aerospace engineers of the 20th century. Here's our roadmap for today's explainer. First, we'll look at the quest for precision. Then, a quick history of guided missiles. After that, we'll break down the two main families of guidance: GOT systems for chasing targets, and goalless systems for navigating space. Finally, we'll wrap up with the limits of perfect accuracy. Let's jump right into Section 1, the quest for precision, and the ultimate navigational challenge. At its very core, missile guidance is trying to solve one massive, incredibly difficult engineering problem. How do you reliably hit something from extreme distances without a human pilot sitting in the seat? As you'd expect, the earliest attempts to solve this foundational problem were totally chaotic, heavily defined by trial and error. Back in World War I, pioneers like Archibald Lowe, who is often called the father of radio guidance, were experimenting with the very first powered drones. Fast forward to World War II, and the German V-weapons program pushed those boundaries even further, using brand new technologies to strike way outside the limits of conventional artillery. Meanwhile, the American Army Air Forces were busy experimenting with dozens of their own programs, covering everything from flying bombs to glide bombs. It was just this rapid, explosive period of innovation that really set the stage for the Cold War era. Moving right along to Section 2, a history of guided missiles, from science fiction to reality. So tracking this progress, we go from Jules Verne's early concepts right up through the immense pressure cooker of the World Wars. But if you look closely at the timeline, there's a really sharp dip right around 1946. Development actually stalled out for a bit. It wasn't until the Korean War kicked off in the early 1950s that American development rapidly accelerated again. And this intense period of Cold War R&D eventually culminated in the short-range PGM-11 Redstone. That's a huge milestone because the Redstone holds the title of the very first U.S. ballistic missile equipped with a highly accurate inertial guidance system. But I want to pause on that dip in the timeline for a second because it involves a pretty shocking number: 55%. Right after World War II, in the winter of 1946, President Harry S. Truman ordered massive funding cuts across American Armed Forces research. This event was so devastating to engineers it became known as the Black Christmas of 1946. The Air Staff slashed the guided missile budget by a staggering 55%. By March of the following year, 10 major guided missile projects were completely canceled. It's just fascinating to think that this absolute juggernaut of an engineering field was almost completely derailed right at its inception. Fast forward to today, and all these highly advanced systems can basically be divided into two main categories. It's a really clean taxonomy. First, you have Go Onto Target, or GOT systems. These are specifically designed to chase actively moving targets, like an enemy fighter jet. Second, we have Go Onto Location in Space, or GOLIS systems. These are designed to attack fixed geographical coordinates, like a stationary bunker or a radar installation. Let's dive deeper into that first category in Section 3, Chasing Targets, GOT systems. This is what I like to call the predatory tech. We are talking about highly dynamic technology here. This is what's required to hunt down something that is actively, desperately trying to get away from you. When a missile needs to chase a target, it relies on homing guidance. Honestly, it helps to think of these like a predator relying on its own senses to track a meal. This homing guidance breaks down into three distinct categories. First up is active homing. This is where the missile illuminates the target itself, usually using its own onboard radar system. Then there's semi-active. Here, the missile is actually blind on its own, and it relies entirely on an external source, like a radar dish on the aircraft that launched it, to illuminate the target for it. Finally, we have passive homing. This missile is totally stealthy and silent. It just tracks the target's own natural emissions, like the heat from a jet engine, or it tracks the visual contrast of the target against the background sky. The amazing thing about these homing systems is that they allow for fire-and-forget capabilities. Once it leaves the rail, the missile doesn't necessarily need a ground station to find its prey. It just goes. However, not all missiles are smart enough to think for themselves, and that brings us to command guidance. In this setup, the smarts are kept outside the missile entirely. It requires two absolutely vital links: an information link to figure out where the missile actually is in the sky, and a command link to literally steer it via remote control. But there's a massive catch here. Because command guidance requires the launcher to actively track and illuminate the target with a strong external energy source, it acts exactly like a giant flashlight in a pitch-black room. It completely gives away your position. It can alert the enemy that they're being targeted, giving them precious time to take evasive maneuvers or even launch counterattacks. By using command guidance, the launcher is essentially painting a massive bullseye on its own back.
This brings us to a really fascinating comparison in the world of missile tech: beam riding versus semi-active radar homing, or SAR-H. Now, in beam riding, a radar or laser beam is pointed directly at the target, and sensors on the tail of the missile basically just try to keep the missile inside that beam. The major upside? You can launch multiple missiles along one single beam. But the fatal flaw is that beams naturally spread out over distance, kind of like a cone. So the further the missile goes, the wider the beam gets and the less accurate the missile becomes. SAR-H, on the other hand, is the exact opposite. Because the missile is homing in on the reflection of the radar bouncing off the target, the closer it gets to that target, the stronger the signal becomes, so its precision actually increases right before impact. They are two brilliantly complementary ways to solve the same problem.
All right, let's shift gears completely and move to Section 4, Navigating Space or Goalless Systems, the fixed point. So here, the challenge isn't chasing down a dodging aircraft. The challenge is navigating halfway across the globe to a very specific fixed geographical point using preset data. Think about it like trying to drive across the entire country completely blindfolded, relying on absolutely nothing but a map and your car's speedometer. Engineers solve this blindfolded driving problem using a concept called dead reckoning, which is driven by inertial guidance. An inertial guidance system relies 100% on internal onboard gyroscopes and accelerometers. It measures every single tiny shift in velocity and direction from the exact moment of launch. And here's the kicker. Because all the math is done internally, without ever needing to look outside for a signal, it requires zero external input. That makes inertial guidance completely and utterly unjammable by enemy electronic warfare. Now, if all this sounds like hyper-advanced, classified military jargon, it actually hits a lot closer to home than you might think. This exact same technology was adapted for commercial aviation. Long before GPS was something we all carried around in our pockets, airliners like the Boeing 707 and 747 used slightly less precise ring laser gyroscopes to navigate across featureless oceans. So if you took an international flight a few decades ago, your commercial airliner was essentially using intercontinental ballistic missile technology to find the runway. That's a pretty comforting thought next time you hit turbulence, right? But what happens if you don't actually have a fixed starting point? I mean, silo-based missiles know exactly where they are launching from, but a nuclear submarine moving deep underwater, it doesn't. Enter astro-inertial guidance. This is just an incredible bit of sensor fusion that literally utilizes the stars. Because moving submarines inevitably accumulate tiny navigation errors over time, their missiles use celestial navigation, star positioning, to fine-tune and secretly correct their inertial guidance systems mid-flight. And the mechanics behind this are just breathtaking. Different global superpowers actually engineered slightly different ways to use the cosmos to perfect their strike accuracy. For example, the US Trident missile system achieved this using a single camera, trained to spot just one specific star in its expected position. If the star wasn't perfectly aligned in the lens, the missile instantly knew its internal gyroscopes were slightly off and it mathematically corrected itself. On the other hand, it's widely believed that Soviet submarine missiles tracked two separate stars simultaneously to achieve their navigational fix. It's literal space-age engineering. Bringing it back closer to the Earth's surface, we have TERCOM, or terrain contour matching. Instead of just flying in a straight, high-altitude, predictable line, modern cruise missiles use TERCOM to fly complex 3D routes. The missile comes preloaded with an internal altitude map of the land between its launch site and its target. As it flies, it constantly uses a radar altimeter to measure the hills and valleys directly below it. It matches those live readings against its internal map to constantly verify its location. This is what allows cruise missiles to fly dangerously low, literally hugging the Earth to hide from enemy radar. But you know what? Even Terracom is being supplanted by something even more advanced, DSACAC. That stands for Digital Scene Matching Area Correlator. With DSACAC, the missile doesn't just measure altitude, it actually uses a camera to look at the ground. Step 1, it takes a picture. Step 2, it digitizes the view. Step 3, it compares that fresh image to stored visual scenes in its onboard computer. And finally, it uses that exact match to guide itself straight to the target. It is essentially playing a high-stakes game of matching photographs in real time while flying at hundreds of miles an hour, just to ensure it hits the exact right building. And that brings us to Section 5, our final section for today, the limits of perfect accuracy and the fragile reality. We have just looked at over a century of mind-bending technological evolution, from sci-fi concepts to navigating by the stars to matching digital photographs at supersonic speeds. But I want to leave you with a really fascinating irony to ponder. If a highly advanced DSMX system relies completely on matching its internal camera to prominent landmarks and buildings, what happens if a preceding missile has just destroyed those exact buildings? The answer? The system can become utterly confused. It lacks robustness in a dynamic environment. It's a stark reminder of the fragile reality of high-tech warfare. Even the absolute pinnacle of guidance engineering can be instantly undone by the unpredictable chaos of the battlefield. It really makes you wonder, what other unseen vulnerabilities are hiding inside tomorrow's weapon systems? Well, that wraps up our explainer on the taxonomy of precision. Thanks for joining us, and we'll see you in the next one.